Welcome to Study Loop.
Okay, so for this question, we have a rod here, we have a point mass here, right? The length of the rod is L, capital L, and the distance between this end to the point mass is x, right? So if we only take a tiny part from the rod here, like this shadow part, suppose the length of it is very small, we call it dl, and the mass of it is dm, right? The distance from this point, from this tiny part to the right end is small l. So this dm, the mass of the tiny part, is equal to the density of the rod, which is the total mass over the total length, times the length of it. So this is the expression of the mass of this tiny part. So first, we need to calculate what's the gravitational potential between this shadow part and this point mass. Then we take the integral to find what's the total potential from the whole row to this point mass. So first, if we only look at this point mass, so according to the equation of gravitational potential, is equal to negative constant g times the mass of the point mass, the mass of this tiny part, which is here dm, divided by the distance between them. The distance between them is the distance x here plus the distance from this point mass, from this shadow part to its right end. So it's L plus x. Right. Now we do the integral on L. So the range of L, it varies from the right end, which is 0, to the left end, which is capital L, right? So we put this equation here. We do the integral from 0 to L on dl, and we can get the expression negative g small m capital M over the length of the rod times the natural log 1 plus L over x. So when x is way much larger than L, this term becomes very small, close to 0. And this ln 1 plus a very, very small number is close to the very small number itself. So the expression becomes negative g, the mass of the point mass, mass of the rod over the length of the rod times the length of the rod divided by x, the distance between the right end of the rod and the point mass. We have L get cancelled. We have the final expression of the potential is negative g small m capital M over x. Okay, that's for question A. Okay, for question B, we're given that the force is negative partial potential divided partial x, right? So basically, this is the derivative of potential by x. So we plug this form into here, we'll get that the force is equal to negative g small m capital M times divided by x squared. This is true when x is way much larger than L.